calculation for chemical engineering. So in previous lecture we have discussed about unit and dimension and the system of unit. So today we are going to study a very powerful tools used in chemical engineering, that is called as the dimensional analysis. It's a very important thing, and the fundamental is based on the unit and dimension. So you have understood how you convert one unit to another unit, then this particular lecture will be very easy for you. So let's try to understand the dimensional analysis. So when we talk about the dimensional analysis, it's extremely important in the areas such as your fluid flow, you will be studying your heat transfer subject, mass transfer, right? And somewhere you can see that there is a chemical reaction engineering. So in all of these subjects you will see it becomes very important to understand the dimensional analysis. So why it is required? So in many practical engineering problems, we know that there are various variables that affect the system, but deriving an exact theoretical equation relating to these variables becomes very difficult, right? So let's say if I want to understand the heat transfer in a circular pipe, let's say if you have a circular pipe, if this is circular pipe and if a fluid is flowing in the circular pipe at a temperature, let's say T inlet, and here the temperature of the fluid is T exit, right? And if the length of this circular pipe is L, and if I am assuming the diameter of this circular pipe is D, so if fluid is flowing, then definitely this fluid will be having some viscosity, density. Fluid will be flowing with the velocity of average velocity and all of these things. So the heat transfer, in this particular thing, or let's say if we want to find out the heat transfer rate, or how much heat transfer is being there, or what would be the temperature of the fluid at a particular length in in the pipe, okay, that becomes very, very important here. So in order to understand these things, you will see that the heat transfer coefficient, let's say H, that will be a function of various parameters over here, like diameter of the pipe, viscosity of the fluid, fluid velocity, let's say U bar, and then density of the fluid, heat capacity of the fluid, and the thermal conductivity of the fluid. Is that clear? So the heat transfer coefficient is a function of various parameters. So if you'll see the parameters over there, so there are 1, 2, 3, 4, 5, 6 parameters, right? Now imagine trying to derive a complete mathematical equation that will relate all these variables directly. So in a real scenario, what you will see that it becomes extremely complicated. That is where the dimensional analysis help us. So dimensional analysis basically bridge the gap between the pure experimental method and the complete theoretical method. So if you have a pure experiment, and then there will be complete theoretical analysis, right? Complete theoretical analysis. So these dimensional analysis basically it bridges the gap between these pure experiments and the complete theoretical things, right? So it provides a systematic method, for studying relationship between variables without driving complicated equation from this particular principle. So the basic principle behind dimensional analysis is called the dimensional similarity. So first I'll be talking about dimensional similarity. Right. So according to dimensional similarity, what happens? So this principle, so any physical equation must be dimensionally homogeneous. So this basically tells you any physical equation must be dimensionally homogeneous. What does that mean? That is very important to understand. So it means that every term in a physical quantity or physical equation must have the same dimensions, right? So let's say if I am talking about velocity u equals to length divided by time. So in the left side the unit should be in meter per second, right? And here also you will see that length unit is meter and time is unit is second, so that will be also in meter per second. So both sides, if you will see here, that the dimension is homogeneous. That is what the dimensional similarity tells us. So another example can be S is equals to, let's say, ut plus half at square. So S is length, right? That will be in meter. What is u? U is in meter per second into second. A is your meter per second square into second square. So if you will do the calculation, this will get cancelled out, this will get cancelled out. So here unit is in meter, here it is also in meter, here it is also in meter. So this validates the dimensional homogeneity, because dimensions of all terms in each side is same from left hand side and right hand side. So in a physical equation, basically you will see that dimensions of all equations should be same, right? I hope this is clear to all of you. Okay, now moving towards the next thing, that let's say, for example, if I take, for example, let's say velocity. So, already I have defined this thing. So now another important advantage of dimensional analysis is that it helps us to reduce number of variables in a problem. So here I'll write this important point, because sometimes you might be asked in the interview. Another important advantage dimensional analysis is that it helps us reduce number of variables in a problem, right? That is most important thing for this. So let's take an example for the heat transfer in a pipe again, right? So what I was discussing earlier, so you have a circular pipe having length is L and the diameter of this pipe is D, let's say. Okay, suppose the heat transfer coefficient depends upon the following variable. So let's say you have a fluid flowing in this with the velocity u, and density will be rho and viscosity will be mu. So the heat transfer coefficient, that will be a function of your pipe diameter d, already I have told you, fluid viscosity, fluid velocity, fluid density, heat capacity, and then thermal conductivity. So K is your thermal conductivity. So we have seen that there are many variables that is going to influence the system, right? So out of that, you can see there are 6 variables that is going to influence the system. So now if we want to experimentally study the effect of each variable separately, right? So we would have to conduct a very large number of experiments. So for instance, if we vary velocity from 1 meter per second to 30 meter per second, so if you want to change velocity from 1 meter per second to 30 meter per second while keeping another parameter constant. So if you only vary the velocity here and another parameter you want to make it constant, so we may obtain heat transfer data for pipe of 25 any diameter, right? But if we change the pipe diameter to another, let's say from 30 diameter to 50 diameter, so the previous experiment data may not be directly applicable, right? Because the data or the heat transfer coefficient that you will be getting from this particular data at a particular diameter, that will be fixed. But if you are changing another parameter, then again you have to do another experiments, right? So here what we have observed, that we would have to conduct another set of experiments, and this quickly becomes time consuming and very expensive. It's not very easy to perform all these experiments, and it will take so much time and money. So that is where dimensional analysis solves this problem, by grouping variables into dimensionless parameters. So for example here, so fluid flow, let's say, you can say fluid flow, the variable in fluid flow, the variable diameter, velocity, density, and your viscosity combine to form an important dimensionless number that is known as the Reynolds number. So basically what we do in dimensional analysis, we combine all of these parameters, all these 4 parameters in fluid flow, and then we make a dimensionless number that is called as the Reynolds number, right? And then we can define the Reynolds number directly, that is equals to density into U into diameter of pipe divided by mu. So now you can see here that we have reduced 4 variable into 1, right? 4 parameter into 1 parameter only. And now I'll change only 1 parameter, and based on the change only we can observe the output. So this dimensionless number represents the ratio of inertial force divided by viscous force. So the Reynolds number can be defined as the ratio of inertial force by viscous force. Right, ratio of inertial force by viscous force. So now you must have understood the motivation regarding understanding the dimensionless number or dimensional homogeneity. So similarly in heat transfer problem also we encounter another dimensionless number that is called as the Prandtl number. Then in mass transfer also in heat transfer you study Nusselt number. In mass transfer you study Sherwood number. In mass transfer you also study the Schmidt number. All of these numbers, these are the dimensionless number, and that is made up of various another parameters. So now in order to understanding if you want to understand the effect of the output for various variables, now after dimensionless number we only vary the dimensionless number, and we will see the effect of this dimensionless number over the output, right? So for example, instead of writing this equation involving many individual variables, now we can write a relationship using this dimensionless group directly. So in heat transfer, let's say heat transfer, now what we have observed that heat transfer coefficient was the function of 6 parameter, but now we know the Nusselt number. So Nusselt number will be a function of your Reynolds number and Prandtl number. So now you can see that only while changing the effect while varying the Reynolds number and Prandtl number, we can check the effect of the heat transfer coefficient. effect on the transfer coefficient. That means the Nusselt number is function of Reynolds and Prandtl number. So instead of dealing with the 7 variables, we have reduced the problem into 3-dimensionless number, right? So the systematic way of forming these dimensionless group is given by important theorem that is known as the Buckingham pi theorem. Okay, so I'll end this lecture here only, and in the next lecture I'll start with the Buckingham pi theorem, where we will see that how n number of variables and m number of fundamental dimensions that can be reduced in n minus m dimensionless group, and from where we can derive various parameters. Okay, so with that I would like to end this lecture. I hope everything is clear in this lecture, and my only request is that if you have not subscribed my channel, please do like and subscribe my channel, and also share with your colleagues, so that I'll get some good viewership. That will be working that will definitely work as a motivation for making subsequent lecture. So because this I'm just designing this course as one of the basic courses for the chemical engineers, I'll be talking about each and every fundamental things where I faced some problem when I was doing my bachelor's, right? So in bachelor's, basically in a particular semester you will see lots of 5-6 subjects are there, but out of 5-6 subjects there will be one process calculation and stoichiometry. So we don't focus more about the process calculation and stoichiometry, but in third semester or fourth semester, when your core subject comes, where we start facing the problem. So that's why I am designing this course in such a way that if you missed this particular subject in your college also, or if you have not understood this course, in this particular, with the help of this video lecture series, definitely you are going to understand each and everything. Okay, thank you and stay tuned.